Hello everyone, welcome to this lecture on operational amplifier. Operational amplifier is simply called as Opamp. This is what the Opamp symbol is. Basically, Opamp is a 5-terminal device. It consists of 5 terminals. Out of those 5 terminals, 2 are input terminals and 2 are power supplies and 1 is the output terminal. Out of 2 input terminals, one is the inverting input terminal, which is represented in minus. Another one is non-inverting input terminal, that is represented with plus. Here inverting input is referred as V1 and non-inverting input is referred as V2. And I said we have 2 power supplies here, V plus and V minus. Sometimes we are going to write this as VCC and V minus as VEE. And Opamp will be having single output terminal, that is V out. Why this Opamp is named like this as operational amplifier? The fact is that amplifier is used to perform mathematical operations on electronic signals such as addition, subtraction, integration, differentiation and all. That's why it is named as operational amplifier. As I said, it will be having 5 terminals. Out of those, 2 are input terminals, 2 are power supplies and 1 is output terminal. And how this Opamp is going to give the output V0? What is the relationship between V0 and V2 and V1? If you look at that, it will be act as a difference amplifier. A difference amplifier in the sense it is going to amplify the difference between the 2 input signals. The 2 input signals are V2 and V1. The difference between these 2 is get amplified and will be available at V0. That's why a general expression can be written as V0 is equal to A times V2 minus V1. What is A here? A is the gain of the amplifier. A is the gain into V2 minus V1. That is the difference. This is how we can define Opamp. Opamp is a difference amplifier. It is going to amplify the difference in the input signals with a gain of A. And by using this Opamp, there are many applications we can have like inverting amplifier, non-inverting amplifier, summer, difference amplifier, voltage follower, logarithmic amplifier, integrator, differentiator. Like this, we can make use of this Opamp to make those applications. And if we look at the pin diagram of IC mu A741, this is a 741 IC that represents an Opamp, where we can observe pin number 2 and pin number 3 are input terminals. Inverting input is at pin number 2, non-inverting input at pin number 3, and output port is pin number 6, and plus VCC is 7, minus VCC is 4. And 2 offset nulls are there, pin number 1 and pin number 5, and one no connection port is there, that is pin number 8. This is the pin diagram of mu A741 Opamp. And if the Opamp is ideal, the ideal Opamp characteristics are as follows. This is very important to understand these ideal Opamp characteristics. The first one is input impedance is infinite. The ideal Opamp will be having infinite input impedance, means at the input side the resistance offered by the Opamp is high, it is infinite, means it will not allow the current into the Opamp. And output impedance is 0. Output impedance is 0 in the sense the resistance at the output side is less, so that it will provide the maximum current to the load. And bandwidth is infinite. Bandwidth is infinite means it will allow different frequency of signals as input. Voltage gain is infinite, that is open loop gain is infinite. We can say without any positive and negative feedback, the voltage gain, if you take for an ideal Opamp, it is infinite. And a special quality of this Opamp is that infinite common mode rejection ratio, CMRR, is infinite. Common mode rejection ratio is that the ability of the Opamp to reject the common mode signals. I said in the first slide itself, it is going to amplify the difference between the signals, difference between the two signals V1 and V2. If we apply the common signal for V1 and V2, it is going to reject that signal and output will be 0. CMRR is infinite. It will reject the common signal. Common mode rejection ratio is infinite. And infinite slew rate. As you guys know, slew rate in the sense rate of change of output. The rate of change of output is infinite. Perfect balance. Perfect balance in the sense when there is no input voltage from V1 and V2, output will be 0. 0 offset voltage. And characteristics of Opamp does not change with temperature. It will be temperature independent. These are all the ideal Opamp characteristics. If the Opamp is ideal, practically these values are somewhat finite, and in this slide you can see these are the practical Opamp characteristics, where input impedance is 2 mega ohm, output impedance is about 75 ohm, open loop gain is 10 raised to 5, offset voltage is 1 millivolts, slew rate is 0.5 volts per microsecond, and CMRR is about 70 to 90 dB. These are the practical characteristics of Opamp. And now let us go for the applications of the Opamp as inverting amplifier. Opamp as inverting amplifier. As the name itself says, it is inverting amplifier. This is an amplifier circuit where we have named it as inverting. Why? Because the signal to be amplified is Vi. We are applying to the inverting input terminal of the Opamp. We are applying the signal which is to be amplified is applied to inverting terminal of the Opamp, and non-inverting terminal is grounded. And there will be an limiting resistor series resistance, that is R1, and feedback, negative feedback is given through the resistance RF, and current flowing through R1 is I1, current flowing through RF is IF. And we need to remember one thing is that whatever the voltage available at this V2, here V2 is grounded. So while taking the currents or while applying KVL here, we need to assume or we need to treat this V1 as 0, same as V2. Why? Because of the virtual ground concept, the voltage available at V1 is same as V2, and V2 is grounded. That's why V1 is also 0. Remember this virtual ground concept, where if V2 is grounded, V1 is also taken as 0. If V2 is provided with some voltage at this point or node, V1 will be considered as the same voltage as V2, and the current flowing into the Opamp is 0. That's why ID is equal to 0. ID is equal to 0, which is the current into the Opamp, that is 0. So we can say whatever the current flowing through R1 will flow through RF as IF, and current will not flow into the Opamp. That's why this ID is 0. Now inverting amplifier, if we apply a sinusoidal signal like this, the output will be exactly reverse, looking reverse to that, means the input taken 180 degree phase shift at the output side. Output signal will be 180 degree phase shifted with respect to the input, and it look like an inverted signal. This is inverting amplifier. Now let us derive the expression for output voltage of this inverting amplifier. How to derive the output voltage? With respect to Vi, we need to derive by taking this I1, IF and voltages into account. Okay, the same circuit taken here for reference. The current flowing through this R1, if you look at the current flowing through R1, I1, this I1, sorry, II can be written as Vi minus V1 divided by R1. Vi is the voltage at this end of R1, potential of this end is Vi, here is V1 divided by R1, V divided by R is I. But here what is V1? V1 is 0 because of V2 is grounded. V2 is 0, that's why V1 is 0 because of virtual ground. So that we can substitute in place of V1 it is 0. That's why expression for I becomes, means the current flowing through R1 becomes Vi minus 0 divided by R1. Then current flowing through the feedback path, current flowing through RF is IF. IF can be written as V1 minus V0 divided by RF. V1 minus V0 divided by RF. Again here V1 will be treated as, this node voltage will be 0 because of virtual ground. V2 is grounded, V1 is 0. That's why it is IF is equal to 0 minus V0 divided by RF. And we know that the current flowing through this R1 is I1 and current flowing through RF is IF, and these two are equal. These two are equal. That's why you can equate these two expressions. You can equate these two expressions. V1 by R1 is equal to minus V0 by RF. If we rearrange this expression as V0 by Vi, this becomes minus RF by R1. What is V0 by Vi? It is gain of the amplifier. Output by input is gain of the amplifier. That's why voltage gain of the inverting amplifier V0 by Vi is AF, that is minus RF by R1. Means the voltage gain of the inverting amplifier will be depending on the feedback resistance and the series resistance values. And if you write the expression for V0, it becomes minus RF by R1 into VL. Here we can observe a negative sign is there at the expression of V0. This negative sign indicates the signal is inverted at the output. This is inverting amplifier. Similarly, we can have non-inverting amplifier. Non-inverting amplifier, we are applying the signal to be amplified, that is Vi, to the non-inverting terminal of the Opamp, and inverting terminal is grounded. Inverting terminal is grounded, and because of this Vi, the voltage available at V2 is Vi, and here the virtual ground concept becomes virtually shorted. So in place of V1 also we can take Vi. V2 is same as Vi, so that these two are virtually shorted. V1 is Vi. In place of V1, while deriving the expression for V0, we need to consider Vi. And this is a non-inverting amplifier. If we apply the sinusoidal signal like this, the output will be amplified and the phase shift is 0. Zero phase shift occurs here. That's why it is look like same as a sinusoidal signal with an amplified output. And now let us derive the expression for V0. If we derive the expression for V0, we need to consider the current flowing through R1 and current flowing through RF, and these two currents are equal. Here in the figure the directions are reversed. Actually the current flow direction for RF will be in this direction, V0 to V1. Similarly the current flowing through R1 is V1 to ground. Here it is put it in a reverse direction, make it as in right to left in this direction. Okay. Okay, now the currents IF and I can be written as, current IF can be written as V0 minus V1. IF is the current of the feedback path, that is V0 minus V1 divided by RF. Similarly I can be written as V1 minus 0 divided by R1. In place of V1 we need to take Vi. Okay, Vi minus 0 divided by R1, V0 minus V1. In place of V1 we can take Vi divided by RF. Again, if you rearrange this and if you simplify, it becomes Vi by R1 plus Vi by RF is equal to V0 by RF. So if you take Vi as common, 1 by RF plus 1 by R1 plus 1 by RF is equal to V0 by RF. V0 by RF will be equal to the same expression. Here it is taken left and right. This gives the expression for V0 as Vi into RF by R1 plus RF by RF. RF get cancelled, it becomes 1. So the final expression for V0 will be 1 plus RF by R1 into Vi. Vi times 1 plus RF by R1. Here also the output voltage of the non-inverting amplifier depending on RF and R1 ratios. And if we write the expression for gain, it is purely plus 1 plus RF by R1. Here the gain is positive. So gain is positive. If you look at the output waveform, it is not inverted. It is same as the input with amplified manner. This is the non-inverting amplifier. And the application of the inverting amplifier is Opamp summer. Opamp summer or adder, or it will be called as weighted summer also. And this Opamp summer or adder is an application of inverting amplifier. Why? Because the Opamp summer is designed by using an inverting configuration. If you look at this part of circuit, leaving these three, it will look like an inverting amplifier, right? But here V1, V2, V3 are connected in a manner to the inverting terminal. For inverting terminal, we have connected V1 through R1, V2 through R2 and V3 through R3. And now let us derive the expression for V0, how actually it will be work as summer we'll see. What is the expression for current I1? Current I1 through R1. I1 can be written as V1 minus V divided by R1. But what is V here? The non-inverting terminal is grounded. Because of virtual ground, this terminal voltage is 0. It's fine. Current I1 is V1 by R1, current I2 is V2 by R2, current I3 is V3 by R3. That is what written over here, the three currents. And what is IF? IF is the feedback current flowing from this end to this end. Again, this terminal voltage is 0, V minus V0 divided by RF. Since it is 0, 0 minus V0 divided by RF. So minus V0 by RF is the expression for IF. And again, the total current I1 plus I2 plus I3 is equal to IF. I1 plus I2 plus I3 flow through this path, and the same current will flow through IF. That's why IF will be equal to I1 plus I2 plus I3. If we equate these currents, we can get the expression for V0. V0 by RF with a negative sign will be equal to V1 by R1 plus V2 by R2 plus V3 by R3. And V0 will be equal to minus, if you take minus to the right and RF to the right, it becomes minus V1 RF by R1 minus V2 RF by R2 minus V3 RF by R3. If we choose all these three resistors equally, if we choose three resistance equal to R, the expressions becomes V0 is equal to minus RF by R into V1 plus V2 plus V3. Now the expression of this Opamp summer becomes minus RF by R into V1 plus V2 plus V3. That's why it is called as an weighted summer. Here this RF by R1, RF by R2, RF by R3 are the weights with respect to V1, V2, V3. If you choose R1, R2, R3 are equal, RF by R is the weight for V1 plus V2 plus V3. And if we choose these three are equal to this RF, R is equal to RF, then output expression becomes V0 is equal to minus V1 plus V2 plus V3. Addition of these three with negative sign, that is the output V0. Here the sum of the input voltages is the result, but the sign is negative. Why? Because it is inverting amplifier's application. They are using an inverting amplifier here to design a summer. That's why here also the output expression will be having a negative sign. This is Opamp summer. And then we have voltage follower. As the name itself says, voltage follower, in the sense the output is going to follow the input voltage. Output voltage will be same as the input voltage. Here this voltage follower is an application of non-inverting amplifier. It is an application of non-inverting amplifier configuration. If you remember the gain expression for non-inverting amplifier, it is 1 plus RF by R1. where RF is the feedback resistance, R1 is the resistance at the inverting terminal. But here RF is 0 and there is no R1, this is open, that's why it is treated as infinite. RF is 0 and R1 is infinite. It becomes 1 plus 0 by infinite, so that the gain is 1. AF is equal to V0 by Vi, that will be equal to 1 plus RF by R1. In place of RF, there is no RF here, that's why it is 0, and no connection towards R1, we can treat it as maximum resistance towards this end, that's why it is infinite, so that gain becomes 1. If the gain is 1 in the sense, V0 will be same as Vi. V0 by Vi is equal to 1, that is gain is equal to 1. So V0 is going to follow Vi. If you look at the waveform, it is exactly same as the input signal. This is voltage follower.